For the few of you that are here, happy Valentine's Day. I'm going to say this, that if attendance doesn't improve by tomorrow, I'm going to stop posting notes. And I will email everybody to that effect, yeah.
Today might be a fluke. The northbound train is...
What about yesterday?
See, it's things like that.
That was equally bad. I'm not satisfied with the attendance. And what the idea is here, on the part of some people, that you can learn chemical engineering passively. You can't. You need to participate actively in order. Maybe political science, you can do that, but CHEME is not a subject like that. So you actually need to show up, take notes, look at your notes, and so on, rather than wait and then look at them afterwards, or not. I don't know what you do afterwards, but I'm tired of it. It's a lot of work for me to do this. I would much rather work on the board. And so if people are not going to attend class, I need to try to motivate them to do so. And what that means is that starting next week, I'm going to not record lectures if I don't get some boost in attendance. So for the few that are here, it doesn't apply. You're here. So I'm going to send an email out to the rest of the folks to this effect. And I'll remind you that we've got a quiz coming up Friday, so we'll see if they show up for that. I'm not sure. But it's quite disappointing to me. What we've been working on here is vapor-liquid equilibrium, and I introduced and derived yesterday the very important Gibbs-Duhem equation. This gives us a relationship between the activity coefficients. So at constant temperature and pressure for a binary, the form that the Gibbs-Duhem equation takes is given here. Now I should pause and say something about this before going further, and that is, if we are paying attention to the Gibbs phase rule, what I've got here is one phase and two components, so I've only got 1 degree of freedom. That means I can fix one variable while I vary another one. So I can fix either temperature or pressure and vary composition. But here what I'm doing is fixing both, so we should recognize at least that I'm making an approximation there that is not, strictly speaking, valid. Now, given that, this is a very important differential equation that relates the two activity coefficients to one another. Yeah?
When would that approximation not work? Or the keeping them both constant?
The most important place where that doesn't work is when we have a very wide temperature variation from one end to the whatever the maximum and minimum temperatures are. And it starts to get bad if it's more than a difference of about 10 or 15 degrees. It's fairly conservative, but many of the systems we work with conform to it well enough. Now, this is a differential equation, so in order to integrate it, we need a constant of integration, and we've got that because we have the limiting conditions here. We have that gamma 1 goes to 1 when x1 goes to 1. Yeah, or we similarly have the gamma 2 goes to 1 as its mole fraction goes to 1. So that means we've got the constant of integration, and the Gibbs-Duhem equation in this form can be integrated. Given this, we can use it in two very important ways, one of which is to check internal consistency of given VLE data sets, of which there are thousands of them tabulated in the literature. And most of them have been cleaned up now, but in the early days there were a lot of them that turned out not to be consistent. They had to be then thrown out. And the next thing we can do is to extend data. If we happen to have knowledge of one of the activity coefficients but not the other, then I might be able to use the Gibbs-Duhem equation to derive the missing one. And let me give you an example of when that might be the case. We might have a solution in which one of the components is not volatile. So we have no way of measuring its composition in the vapor phase because it isn't present in the vapor phase. And yet it's going to have activity coefficients. So what we do is measure the pressure above the solution, identify it with the volatile component. That'll be enough to give us gamma 1, say, and then we could use the Gibbs-Duhem equation to derive gamma 2. One of the quick things we can do with this now is to validate what I stated without proof here earlier, and that is that we have either cleanly positive or cleanly negative deviations from ideality, which means that if gamma 1 is greater than 1, so is gamma 2 across the composition range. And similarly, if one of them is less than 1, so must the other one be. So let's just prove that right now. And we can do that by just rewriting the Gibbs-Duhem equation in the following form: divide through by dx1, and then look at the plots we have for logarithms of the activity coefficients versus composition. If I have over here d log 1 dx1, I see that that has got a negative slope. So that means I know that gamma 2 is going to have to start here, and the question is, does it go down or does it go up? But what this equation tells me is that it has to have a slope opposite to the slope of d log gamma 1 dx1, so it has no choice except to go up like that. So I've therefore proved the assertion that I made earlier just based on this Gibbs-Duhem equation. But now let's look at the more important general issue here of extending data. Now let's assume that we've got gamma 1 here as a function of x1 for a binary solution, and we'd like then to derive gamma 2. Well, I can write d log gamma 2 here in terms of the Gibbs-Duhem equation. It's just then minus x1 over x2. But I can write this more conveniently as d log gamma 1 dx1, as I've done over here, times dx1, and then integrate on x1. So I'll indicate that integration here. D log gamma 2 integrated from x1 equals 0 up to some indefinite x1. And integrate over the same limits here on the right-hand side of the equation. So let's take a look at this left-hand side, and we'll notice that log gamma 2 at x1 is just going to be the value we seek, so that's just log gamma 2 at that particular value. But log gamma 2 at x1 equals 0, let's look at that. At x1 equals 0, x2 equals 1, and the log of 1 is 0. So this whole thing is just 0. So what I have on the left-hand side here is just cleanly log gamma 2 at the particular x1 of interest. So let's look at the right-hand side, integrating that. So if I have an expression for log gamma 1 as a function of the mole fraction, then I can prepare this derivative, put it in, and then integrate. Well, let's look at a simple situation here. I'll repeat the equation over on the right-hand side. And as an example, let's assume that log gamma 1 can be represented by a simple quadratic expression. A is just a constant here, some empirical constant that we use to fit the data, times x2 squared. And if I look at data that I had before for a particular example system, that doesn't look too bad. Those equations look like they could be fit by a simple quadratic. So we're not out of the ballpark to make the possible assumption that something like that could be realistic. Well, if this is the case, that log gamma 1 is given by this function as empirically obtained by fitting data, then d log gamma 1 dx1, I'll just differentiate that, and I see it's equal to minus 2a times x2, just working it out. And so that then would go up in here, and I can indicate that just by cleaning things out. The minuses cancel each other, x2's cancel each other, and I just end up with 2a times the integral of x1 dx1 between 0 and x1, leaving me finally with a x1 squared. So that's interesting. I've got log gamma 2 is a x1 squared, and we recall that log gamma 1 was equal to a x2 squared. In other words, go as the square of the opposite mole fraction. Now it can be said that there are actually some systems that obey this. In other words, I have fit the ideality, non-ideality, in terms of a single constant a in this case. And I can't more often than not, I can't do that. That just isn't complex enough to be able to fit the kind of data that we may see. So we'll have to see how to deal with that. So I'd say here most systems require 2 parameters for a successful correlation. And now we have to think about how we would do this. Well, imagine I have data that I will have essentially activity coefficient data for both components. And I can think about fitting them maybe to a power series. I kind of got the idea now that series better start with a squared term, and that actually can be proved. And then I can go from there looking at one and then deriving the other, even though I have data for both. Well, that doesn't seem right, why you prefer one over the other to fit and derive the missing one. So we have another way to do it, and that is to invent a function, turns out to be extremely useful, that embraces both activity coefficients on an equal basis. So we'll look after not two functions, but a single function that embraces both of them. And in a sense, that function that we're going to look for is an integrated form of the Gibbs-Duhem equation. But we call these things thermodynamic excess functions, and I'll take whatever time it needs for us to get clear on what these things mean. Now, for any molar extensive thermodynamic property, we can define a molar excess function in the following way. So here is the molar excess enthalpy, and it is defined as the molar enthalpy change of mixing minus the molar enthalpy change of mixing that we would have if it were an ideal solution. That is, the gammas are all are all equal to 1. Here, this is just going to, we know that that ideal one is just 0, so that's how it works out, that the excess molar enthalpy is just equal to the molar enthalpy change of mixing. And the same thing for excess molar volume, defined exactly the same way, the molar volume change of mixing minus the corresponding molar volume change of mixing if it were an ideal solution. But we're not really too interested in these things or any of the other ones. The one that we're really interested in is the excess Gibbs energy. And that's defined as the molar Gibbs free energy change of mixing minus the molar Gibbs free energy change of mixing if it were an ideal solution. And maybe you can see right now what that does. That pulls out all of the compositional dependence, and it'll give us a function that expresses just the non-ideality. So let's write it out. We have an expression here for the general Gibbs free energy change of mixing. That's what this is. And then the case for the ideal is here. And so we're left with this as the expression for the molar Gibbs free energy change of mixing. So this, you can see right away, this will embrace the activity coefficients of the components on equal footing. If I write it out for a binary, then this is what it looks like. So what our goal might be in fitting data would be to fit data to a function for the excess Gibbs energy. So if we know this excess Gibbs energy is a function of composition at a given temperature and pressure, it's important to recognize that we know everything about the non-ideality of the system. Which means that if we had that function, some function of x1, I should be able to derive from it in a systematic manner the activity coefficients gamma 1 and gamma 2. So let's explore that. So the idea here, here's the function that I've got, and it's got gamma 1 and gamma 2 in them, or in it. And now I'll multiply through by n, so here I have nge over RT. That turns into an extensive function. So what that is the extensive Gibbs free energy of mixing over RT. Then I can differentiate that with respect to n1 and n2, respectively, and pull out directly the logs of the activity coefficient. So this is a very important equation. It tells us that once we have an expression, an algebraic expression for the excess Gibbs energy, then I can extract from it the activity coefficients. So that you can see that just looking at this function. And is everybody okay with this? It just has a little bit of an awkward look to it. And we can do the same thing then for log gamma 2. So this is the aim here is to use a VLE database to get a function GE as a function of composition. So if that's the situation, let's examine the nature of GE mathematically. And in particular, let's see what it has to be at the extremes of x1 equals 0 and x1 equals 1. If x1 equals 0, let's write it out. Then I've got 0 times log gamma 1. That log gamma 1 is going to be the limiting value, but I see that that's 0. And the second term, x2 times log of gamma 2, well, gamma 2 at x1 equals 0 is equal to 1, which is also 0, so we see that at x1 equals 0, the excess Gibbs energy must be 0. And similarly, and not surprisingly, I have the same situation existing at the other extreme. At x1 equal 1, then I've got 1 times log gamma 1, so that's 0, and here I've got 0 out front. That's just this, so 0, and that is 0. So whatever function we choose, whatever functional form we choose to represent the excess Gibbs energy, it's going to have to go to 0 at both extremes of the composition range. The simplest thing we can choose for that would look like this. If we tried to diagram this function, it might look something like this. For positive deviations, we'd expect the excess Gibbs energy to be positive over the whole composition range. If they're negative deviations, we're going to have something which is negative over that composition range. So this is 0 in both cases here. But the simplest function that we can have, and I purposely made that unsymmetrical, if this were this function, then these would look like symmetrical functions. But more often than not, they are not. So I purposely made them a little lopsided. But this is the simplest function we might be able to propose. Obviously, that's guaranteed to go to 0 at either end of the composition range. So let's go through the process of, from this excess Gibbs energy function, deriving the expressions for log gamma 1 and log gamma 2. So the first thing is to multiply through by n, so we get an extensive function. Then I've got some excess n's here. So it ends up looking like this. Then that's going to be differentiated with respect to n1 and then with respect to n2. So differentiated with respect to n1 to get log gamma 1, here's the operation. Carrying out that differentiation, remembering that I'm going to end up with 2 terms, because n itself is a function of n1. Looks like this. Writing it out every step, I see that, whoa, look what I end up with. I get a x2 squared, so just what I had proposed before. I could go through the same process for n2, but you can see right away that it's going to end up in the same place. So log gamma 2 is going to be a times the square of the other mole fraction, x1. If this were the case, and I've suggested that it sometimes is, but that's fairly rare, a should be a constant over the whole composition range. Now, when I prepare the data set, I have a VLE data set that's going to have 3 columns of data, x1, y1, and either t or p, depending on what is constant. If I go through that composition range, it suggests that if I make a column to calculate GE over x1, x2, RT, that should be just this constant A. So let's take a typical system here and examine what we might get. This is a system of methyl ethyl ketone and toluene at 50 degrees C, so it's a constant temperature system. So here's my column of, these are the data that come out of the literature. You notice here that at x1 equals 0, then that the pressure is just going to be the vapor pressure of the other component, namely of component 2. And similarly down here, when x1 equals 1, then the total pressure is just going to be that vapor pressure. Well, I can, as we've shown before, using modified Raoult's law, I can calculate gamma 1 and gamma 2, and hence log gamma 1 and log gamma 2. And you can make as many columns as you want in the spreadsheet to keep things simple. But once I've got those two, I can calculate this thing, because this is going to be GE over RT. Remember, it's just going to be x1 log gamma 1 plus x2 log gamma 2. Let me back up to just validate that. Got it here somewhere. Where in the world have we got it? Yeah, here. So GE over RT is just x1 log gamma 1 plus x2 log gamma 2. So I can calculate that just, by doing column operations here in my spreadsheet, and calculate that for every mole fraction here, x1. And then I can divide through by GE over RT, divide that through by the product x1 times x2, and see if this is in fact a constant. If that simple representation that I proposed was true, then this should be constant, and I clearly see that it's not. But if I examine these numbers, then what I notice is that they're monotonically decreasing. So it suggests to me that they perhaps might be fit by a linear relationship. So I will try that out. I'll try a plot here of GE over x1, x2, RT versus x1, and see how close I get to a straight line, and not bad. Looks like there are a couple of slightly errant points here, but I can call that a reasonable straight line. And this is really convenient for us because now out of that straight line I can extract a linear relationship, in other words, a two constant relationship for the logs of the activity coefficients, and I can use linear least squares, which is especially convenient to do this. So let me try that and see what happens. So it's convenient to express least squares representation here, and I'm going to write it this way because this is the way it's common to do. So I'll write out this linear relationship as a constant a21 x1 plus a constant a12 x2. And this is the way that it is common to label these, and everybody does that now. Obviously, I could have done something else. I could write a x1 plus b or something like that. It's clear that this is a linear function, but the way we identify the constants is the way I've shown you here. So what we see right away is that we can identify from the least squares plot like this that the intercepts will give us directly what these constants are. And they turn out to be 0.372 and 0.198 for this system respectively. So now I've got the same plot I had on the previous slide, except here now I've represented it this way as a linear function. I've identified the intercepts here by extrapolating to the extremes, getting the values of the constants, and I should be good to go here. Any questions before I go further? Yeah.
If you scroll up a little bit, I just want to make sure, on the right-hand side of the equation at the top, is that an A21 or is that like a G or something? That's a 2, right?
This is A21, yeah.
Okay. Just want to make sure.
Okay. So our next job would then be to extract expressions for the logs of the activity coefficients. So if I go through the process that I identified before, and that would be perhaps a useful exercise for you to do, this is what I end up with. I get log gamma 1 in this interesting form. It's x2 squared, now not just times a12, but a12 plus 2 times the difference in these constants times x1. And log gamma 2 is equal to x1 squared times the constant a21, which is now different from a12, plus this, you'll notice this is just the negative of the top one. And if I plug in the numbers that I've got here for a12 and a21, this is what I end up to describe this particular system that I have, which I already forgot what it was. Methylethyl ketone and toluene. These important equations are called the Margules equations. And if we write out this thing, if I substitute in for, let's say, x1 is 1 minus x2, or x2 is 1 minus x1, what I notice is that these Margules expressions will give us the logs of the activity coefficients as cubic functions in the opposite mole fraction. And therefore, they are sometimes called the 3 suffix Margules equations. And if it happened that a21 and a12 are equal to each other, then these terms, of course, would go out, and I'm just left with these, and they're equal, and I go back to that original formulation where I just have a single constant a.